Now, in the topic of nuclear physics, we're going to learn about the nucleus. That's why we call it nuclear physics. And whenever we talk about the nucleus, we talk about these particles which are very small. For example, like electrons, neutrons, protons, and all those. So their masses are actually very small. So in terms of kg, it will be too small, like 10 to the power negative 27 kg, the biggest like that. So in order to make the mass a bit small, the numbers are a bit nicer to see, so they actually use the unified atomic mass unit to measure the mass. So they measure all the masses in terms of U. So what is 1 U? Can you remember 1 U? 1 U is 1.66 times 10 to the power negative 27 kg. So all these masses that are given in this table are all in terms of U. Okay, so if they give you the mass in terms of U, you just have to know how to convert to kg. So you just times this. But if you want to change from kg to U, then you divide by this. Okay, okay, this is a unified atomic mass unit. Alright, by definition, they actually ask this definition of 1U. What is the definition of 1U? It is the 1/12 of the mass of carbon 12 atom. Alright, so, and what is 1 mole? What is 1 mole of substance? The one is in own ideal gas also lah. It is it contains Na number of atoms, right? Not 1 mole of substance contains Na, which is Avogadro constant number of atoms of molecules. Alright, so anyway, so let's talk about missing mass and binding energy now. Let's give an example, an alpha particle. You know an alpha particle is made out of what? How many protons, how many neutrons? 2 protons and 2 neutrons, right? So I want you to take from the table the mass of 2 protons. That means you take this times 2, and then you add with these 2 neutrons. That means this times 2. So you add up 2 times this plus 2 times this. What do you get? See whether or not you can get this mass of alpha particle here. And if you do that, you will realize that the number is not the same. How much is the difference? The difference is about 0.030377 U. But which is bigger? The mass of 2 neutrons and 2 protons, or the mass of 1 alpha? 2 neutrons, 2 protons are actually heavier than 1 alpha particle, which doesn't make sense, right? Not because 2 neutrons and 2 protons make up a alpha. But why is it these 2 neutrons and protons are heavier than the alpha? It's because of what Einstein said happened. His theory, his famous equation E equals mc squared. So this is how he explained it. So he was saying this. The 2 neutrons and 2 protons, they are actually far away. They're infinite distance from each other when they started. But to come together to form a nucleus, a lot of work has to be done. Understand? Especially, when you consider the 2 protons are positive and repulsive, and you place them in such a tiny space. Remember we learned in your AS Rutherford's alpha scattering experiment, your nucleus is very, very small. So imagine you squeeze in 2 protons which are positively charged and wants to repel each other into a tiny space. How do you manage to do that? If let's say you got 2 people who hate each other, how are you going to force them to share the same car? Right? Sit in the same car for 5 hours. Right? You must do a lot of work. A lot of effort must have been used to force them to sit together. Right? So that is what I'm trying to say. So, but then, in order to do the work, you need energy. A lot of energy needs to be supplied in order for this to happen. But who supplied the energy? That's the question. So Einstein explained it by saying that the masses of this, it means the 2 protons and 2 neutrons, what they did was they each of them sacrificed some of their mass to convert it into energy. So Einstein says the mass and energy can be converted, alright, using his famous equation E equals mc squared. So the E is the energy, the mass is the one you convert into energy. So each of them sacrificed some of their mass, became energy, and they used up this energy to do the work to come together. So therefore, when they come together, they are lighter. So in an alpha particle, they are lighter. But the reverse is also true. If you wanted to split the alpha particle back into two separate protons and two separate neutrons, you must do exactly the same amount of work, right? So the work that you do on the alpha will then be converted back into their mass. So if you separate them into their two protons and two neutrons, they will regain back their original mass. Do you understand? So this, the difference between the mass of alpha and the two protons and two neutrons, which is actually 0.030377 U, which is actually very small, but you cannot ignore it because it's equivalent to 55 electrons. That means you take this mass and you divide by the mass of an electron. I'm not saying they lost 55 electrons. I'm saying the mass that they lost is equivalent to losing 55 electrons. So it's quite significant. Do you understand? All right? Okay, so if you use Einstein's equation, E equals mc squared. Now the m is not the entire mass, not the entire mass of alpha or the entire mass of proton or neutron. The m here represents the mass defect. And what does mass defect actually mean, right? It's the difference in the mass of the proton and the neutrons two together and the mass of the alpha particle. So you must use the mass defect times the c squared, which is the speed of light in vacuum. So, this is the definition of mass defect. The mass defect is the difference between the total mass of all its separate nucleons. Separate nucleons means the two protons and two neutrons, and the mass of the nucleus itself. Now, then the energy that you calculate from this mass defect. So let's say we take this mass defect with times c squared, right? We will get E. So what does the E represent? The E, in this case, is the energy that you converted from the mass to come together, right? But think about this. If let's say you required, let's say example, 5 electron volts to come together to form a nucleus, right? To separate the nucleus back into two protons and two electrons, two neutrons, sorry, two protons and two neutrons. So how much energy you must apply? Also, 5 electron volts, right? So this is called binding energy. So what's the definition of binding energy? Binding energy is equal to the energy needed to separate the nucleus into individual nucleons completely to infinity. You understand? So this is the definition. You must say that. So binding energy is actually the same the same energy that you will do the work to come together as the energy that you have to supply to break them up. But we always define binding energy as the energy to break them up. Okay? And in the next slide, you will see how is it related to stability. Now, think about how binding energy is related to stability. If you have a higher binding energy means you need more work. That means you need to do more work to separate the nucleus. So is it more stable or less stable? If you need to supply more energy to break it up, there is more stable, right? So the higher the binding energy, the more stable the nucleus. You understand? So binding energy is not the energy that the nucleus has. Binding energy is the energy that you need to supply to split it. So example, I give you the diagram like this. So let's say this is your energy at infinity. So this is the energy you must reach to separate completely. Now let's say you are at this energy level E2. Now E2 is not your binding energy. The energy that you need to supply to bring it to infinity, alright, that is called your binding energy. Do you understand? So if you have another nucleus with a lower energy level, that means more stable or less stable. If it's lower energy level, more stable. Alright, because it contains less energy, so it's actually more stable. Then you would supply more energy to separate it, right? So then the binding energy is higher. So can you see the higher the binding energy, the more stable it is? So that's the idea. Binding energy is not the energy the nucleus has, but binding energy is the energy you need to supply to split it. So if we look at another term called binding energy per nucleon, it is a better indication than binding energy. For example, if you have two nucleus A and B, nucleus A has 3 nucleons and nucleus B have 2 nucleons. The total binding energy for A is 12, the total binding energy for B is 10. If you just compare the binding energy, which one seems more stable? A seems more stable, right? But if you look at binding energy per nucleon, that means you take the binding energy divided by number of nucleons, you will get 12 divided by 3, you get 4, right? And for this, you take 10 divided by 2, you get 5. So which one has higher binding energy per nucleon? You have B. So therefore, which is more stable? B. So it's something like this. Let's say there's 3 best friends together. So in order to because they're so close to each other, if you want to instigate them to fight against each other, to separate, you have to do 4 joules of work on each person. But for another pair of best friends, all right, even though there are only 2 of them, but to separate them, to instigate them to fight, you do 5 joules of work. So which one will you consider a closer friendship? The 5 joules one, so something like that. So you look at binding energy per nucleon. So if you look at the graph here of binding energy per nucleon versus nucleon number, the higher the binding energy per nucleon, the more stable. So which element is the most stable? Can you see it? Iron. Do you understand? All other elements, for example, uranium. Uranium is on the right hand side here. If it wants to be more stable, it wants to have higher binding energy per nucleon, right? So it must move to the left or right to move up the graph. You must move to the left, right? But when you move to the left, can you see the nucleon number decreasing? That means it must become smaller. So therefore, all elements on the right hand side of iron will undergo fission. Because fission means splitting to smaller particles. You see, the objective of any of the radioactive processes, which is fission, fusion, and decay, what are their main objective? To become more stable. Therefore, they must move to the left. This uranium must move to the left. But if you compare, for example, deuterium is on the left-hand side of iron. For it to be more stable, it must move to the left or right? Must move to the right. So move to the right, the nucleon number increases. So therefore, you must undergo fusion. You understand? So you must remember this iron, the number 56, because they ask you to mark like barium, krypton, and all those if you're given nucleon number. So if you know it's 56, anything more than 56 on the right hand side, anything less than 56 on the left hand side. Yes. Okay? Now that's all you need to know. But there's also 3, you see this graph is a smooth graph, but you see 3 points which are peaks here. That means what it indicates is actually helium, according to the nucleon number, should be somewhere here, the stability. But it's actually more stable because of higher binding energy per nucleon. The one you just have to know that the structure of 42He is an exceptionally stable nucleus structure. So therefore, it just is higher than what it's supposed to be. And this oxygen is actually 4 times the structure of helium. See, 4 times 4 gets 16, 2 times 4 get 8. So it's also exceptionally stable. But there's another peak here, which is carbon. Carbon will be what? 12? 6. Which is times 4 times 3, 2 times 3. So these 3 are just outside the general trend because they're just exceptionally stable. That's all. Alright?